Hi everyone, welcome to the part 2 of techniques for computing limits. In this video, we are going to talk about evaluating limits by factoring or rationalizing and then using squeeze theorem. In the previous video, we talked about using direct substitution to find the limit of a function. Sometimes substitution does not immediately work, especially when we get 0 in the denominator. So in this case, we must algebraically manipulate the function first and then do the substitution. So there are mainly two different cases. The first one, we can just factor and simplify the function and do the substitution. And then especially when we have radical, we'll do something called rationalizing, either numerator or denominator, depending on where the radical is. So we are going to look at some examples. So whenever you see a rational function, first what we do is we try to do direct substitution, because if we don't get 0 in the denominator, then we can still do the direct substitution. So for this example, let's go ahead and see that what happens if we do the direct substitution. So if I plug in 3 here, I get 3 squared 9 plus 3 is 12 minus 12 is 0. So I'm getting 0 in the denominator, which means I cannot do direct substitution. So what I have to do is I have to simplify this function and then do the substitution. So usually here, let's see if we can, in this type of functions, we should be able to factor numerator and denominator separately, and we should be able to simplify by canceling. And let's see if we can do that. So this equals limit as x approaches 3. So we have x squared minus 4x plus 3 in the numerator, so we can factor this as x minus 3 times x minus 1. Similarly, we can factor the denominator as x plus 4 times x minus 3. Now we see that we have a common factor in the numerator and the denominator, which is x minus 3. That means we can cancel them. And then we get this equals limit as x approaches 3, x minus 1 over x plus 4. So now we can do the direct substitution. So if we plug in x equals 3, then in the denominator we are going to get 3 plus 4, which is 7, and it's not a 0. So if we don't get 0 in the denominator, it's okay to do the direct substitution. So let's go ahead and do that. So this equals 3 minus 1 over 3 plus 1, then we get 2 over 7. So this is the limit for that function. Now, the other case that we are going to talk is the one with the radical. So if we have something like that, we are going to do a rationalization or multiplying by a conjugate. So conjugate means if you have a plus b and then we multiply by a minus b. So these are conjugate pairs, especially when we have those radicals. Okay, so a plus b and a minus b, these are conjugate pairs. So what we do is here we have square root of x minus 3. So this is like a, and this 3 is like b. So we have a minus b. That means we multiply by the conjugate, which is a plus b. Or in this case, it is times square root of x minus 3 plus 3. So we multiply by this one. So when we multiply the numerator, we must multiply the denominator by the same quantity. So we'll multiply the denominator by x minus 3 plus 3. Now the next step, just be careful. When we multiply, we are going to multiply the conjugate pair, and we leave the other one in the factored form because our goal is to cancel the factors. So if we multiply now, again, we have to factor out. So we leave the other pair as it is in the factored form, but we are going to multiply the conjugate. So we'll multiply the numerator in this case, and we'll leave the denominator in the factored form. So this equals limit as x approaches 12. So we multiply the numerators. So when you multiply conjugate, it's easy multiplication. So if you have a plus b times a minus b, this can be written as a squared minus b squared. So in this case, we can do square root of x minus 3 squared minus 3 squared. You can also do FOIL, but that becomes a little bit more lengthy, so we'll just use this. And the denominator becomes x minus 12 times, so we'll leave them as factored form, in the factored form, so square root of x minus 3 plus 3. So now let's go ahead and simplify the numerator. So limit as x approaches 12, so this is x minus 3 minus 9 divided by x minus 12 times square root of x minus 3 plus 3, and then limit as x approaches 12, so the numerator is x minus 12 over x minus 12 times square root of x minus 3 plus 3. Now we see we have a common factor here, x minus 12, that means we can cancel that. And then we get limit as x approaches 12 of 1 over square root of x minus 3 plus 3. Now if we plug in, or if we do the substitution now, we don't get 0 in the denominator. So we can do the direct substitution now. So this equals, so 1 over, so if I plug in 12, so I have 12 minus 3, which is 9, and the square root of 9 is 3, plus 3, and that gives us 1 over 6. And that is the required limit. So this one is try now problem. What I want you to do is pause the video, try this by yourself, and then check your work by resuming the video. Let's go ahead and do it now. So this equals, now again, the first thing that we are going to try is try to do the direct substitution. If I do that, I'm going to get 4 minus 4, 0 in the denominator. That means I cannot do it. So what I'm going to do here is I'll try to factor and then simplify this expression. So this equals limit as x approaches 4. So let's go ahead and factor the numerator. It is in the form a squared minus b squared, which can be factored out as a plus b times a minus b. So we have x squared minus 16, so we can write x minus 4 times x plus 4 divided by 4 minus x. Now, if you look at these two factors, x minus 4 and 4 minus x, they are very close to similarity, but they are not exactly same. So we cannot cancel them if they are not exactly same. So what I'm going to do is I'm going to factor out -1 from here so that those two factors look exactly same. So let's go ahead and do that. So limit as x approaches 4. So if I factor out -1, then I can write 4 minus x. So now if you distribute that negative, you get the same thing that you have over here, okay? So that times x plus 4 divided by 4 minus x. Now we can do the cancellation. So we can cancel this too. And then that becomes limit as x approaches 4. So now we can multiply this second factor by that negative. So you get negative x minus 4. And then we can do the direct substitution. So when we do that, we get -4 minus 4, and that gives us -8. Now, the next one is a function where we have to multiply by the conjugate because we have this radical here. So now we are going to multiply by the conjugate of the denominator. So we have square root of x plus 5 minus 3. That means we are going to multiply by the square root of x plus 5 plus 3, the conjugate. So we have minus here, so we multiply by the plus, which is the conjugate. Now, when we multiply the denominator, we need to multiply the numerator as well. So we are going to multiply by x plus 5 plus 3. Now that equals limit as x approaches 4. So again, we don't multiply the numerator here because they are not the conjugate pair. So we leave them in factored form. So we just write that as it is. And the denominator we are going to multiply again, multiplying conjugate. It is a plus b times a minus b is a squared minus b squared. So square root of x plus 5 squared is just x plus 5. Then minus 3 squared is 9. So that equals limit as x approaches 4, x minus 4 times square root of x plus 5 plus 3 divided by, so this is x minus 4. Again, we have this common factor here, so we can cancel this too, and then we can do the direct substitution. So now we can substitute that. So square root of 4 plus 5 plus 3, and then 4 plus 5 is 9, square root of 9 is 3, 3 plus 3 is 6. Okay, so another technique to compute limit is using squeeze theorem. This is a little bit tricky, it's a little bit technical, because if we are finding a limit of a function, then we need two other function, okay, such that, so this is what the theorem is saying. So if we have three functions in this order, so we have f of x always less than or equals to g of x, always less than or equals to h of x, and then we can just draw a graph and illustrate that. So for example, we have a function going, let's say, like this. Let's say this is f of x. And then let's say we have another function like this. Let's say this is h of x. And then there's another function, let's say, which is, sorry, this is f of x, and then the red one is g of x. So that means f of x is always, the green one is always less than the red one, and then the red one is always less than the blue one. So in that case, so if we are looking at a limit, if we are looking for a limit and when x approaches to this point here, so we know that the limit as, let's say, x approaches 0, for h of x is 0. So the limit for the top function is 0. Similarly, the limit for the lower bound function, which is f of x, so limit as x approaches 0 of f of x equals 0 as well, because it goes right here. Now, even if we don't have this function here, the rate function here, but if we know this inequality holds for those three functions, now just looking at these two, I can conclude that limit as x approaches 0 of g of x must be 0 by this squeeze theorem. So that's what the squeeze theorem is saying. Okay, so if you have three functions, the middle function is bounded between those two functions, and the limit as x approaches a for these two functions are equal, that means the middle one should be, the limit for the middle one should be same. Okay, so let's look at some examples here. Sometimes this type of problems could be a little bit challenging because now we have limit as x approaches 0 and we are just given one function, but in order to apply this squeeze theorem we need three functions, so we need to have this order. Okay, so whatever the function that you are trying to find limit for, that should be a middle function. That means this is the function that we have in the middle. Now what we need is we need two more functions, one greater than that and other one less than that. So now sometimes it might be challenging to get that, but usually with this trigonometric function it's a little bit easier because we know that the range for sine function is between 1 and -1. Okay, so -1 and 1. So sine function, whatever sine theta or something, whatever we have, so it's always between -1 and 1. So knowing that, we can start setting up that inequality and then we can get the right inequality that we need. Okay, so we know that sine of 1 over x is greater than or equals to -1, and this is less than or equals to 1. This is true for all x's, so for all x except when x is 0. Okay, so this is true for all x's, but not when x is equals to 0, because when x is 0, we get 1 over 0, which is undefined. So we cannot take that one. And it is okay because what we are trying to find is we are trying to find the limit when x approaches 0. It doesn't mean x is equals to 0, okay? Just x is approaching to 0. It's not equal to 0. So this should be good. Now, what we have here is we have x squared times sine of 1 over x. We just have sine 1 over x here. So what we need to get is we need to get that x squared. Now in that inequality, let's go ahead and multiply everything by x squared. And it's okay to do that because x squared is a positive number. So if you multiply by a positive number in an inequality, this sign does not change. The inequality sign does not change and it still stays the same. Okay, so that means if we multiply by x squared, then we get negative x squared is less than or equals x squared of sine 1 over x is less than or equals x squared. Now our goal is to find the limit as x approaches 0 of that function. So let's go ahead and check what we get for these two functions. Do we get the same limit? Can we use this squeeze theorem? So let's go ahead and try that. Okay, so let's say limit as x approaches 0 of negative x squared equals 0 because we can do the direct substitution. Similarly, limit as x approaches 0 of x squared is also 0. We can do the direct substitution. That means it satisfies the squeeze theorem, okay? Because we have the limit for the left side function 0, limit for the right side function 0. Now by squeeze theorem, the limit for the middle function must be 0. So this implies by squeeze theorem, we can write limit as x approaches 0 of x squared times sine of 1 over x must be 0. Let's look at one more example. Now here we are asked to find the limit as x approaches 2 of f of x. Okay, so we don't know what that function is, but we are given the inequality, which is good. So we can try using the squeeze theorem. So let's go ahead and try that. So if we get the same limit for the lower function and the upper function, then we can conclude that the limit for the middle function is also same. Okay, so let's go ahead and do that. So let's go ahead and find the limit as x approaches 2 of the left function or the lower function, which is 3x. And then we know that we can do direct substitution. So this is 3 times 2, which is 6. Now similarly, let's go ahead and find the limit for this function. So limit as x approaches 2 of 2 times x to the fourth minus 2x cubed minus 10 equals, so we can do direct substitution. So 2 times 2 to the fourth minus 2 times 2 cubed minus 10. Okay, so 2 to the fourth is 16 times 2, 32, minus 2 cube is 8 times 2, 16, minus 10. So 32 minus 16 is 16, minus 10 is 6. So we got 6 for the lower function, 6 for the upper function. Now by squeeze theorem, okay, so by squeeze theorem we can say the limit as x approaches 2 of the middle function, which is just f of x, equals 6 as well. We'll just do this much for this video. I'll see you again in the next video.